You step into the past and erase your own existence. This is the famous grandfather paradox, a logical knot that has fascinated thinkers for generations. We are about to dive deep into the mind-bending world of time travel theories, exploring 30 of the most fascinating and scientifically intriguing concepts ever proposed. By the end, you will possess a complete map of the theoretical landscape, from the edge of proven physics to the wildest frontiers of speculation. We will journey through wormholes that twist into tunnels through time, confront paradoxes that threaten to unravel logic itself, and question the very fabric of spacetime. How can an object exist without ever being created? Could every choice you make spawn an entirely new universe? What would you do if you discovered time travel was not just possible, but already happening around you? The answers will challenge everything you think you know about cause and effect. So, if you could witness one moment in history, which would it be? The grandfather paradox presents a perfect logical storm. Picture this scenario. You build a time machine, travel back to a year before your father is born, and prevent your grandfather from ever meeting your grandmother. The immediate consequence seems clear. Your father is never conceived, and therefore you are never born. But if you were never born, who built the time machine? Who traveled back to commit the act? The event that caused your non-existence requires your existence to happen. It is a closed loop of impossibility, a statement that contradicts itself. This is not just a plot device for science fiction. It is a serious challenge from the realm of logic, suggesting that backward time travel might be fundamentally incoherent. It forces us to question whether the universe itself has rules that prevent such contradictions from occurring. One compelling idea to escape this trap is the principle of self-consistency. Proposed by physicist Igor Dmitrievich Novikov, this principle suggests the universe is inherently consistent. You could travel back in time, but you would find it physically impossible to change the past in any way that creates a paradox. Your actions would be constrained, perhaps by unseen forces or sheer coincidence, ensuring history unfolds exactly as it always did. In this view, you are always part of your grandfather's past. Your attempt to interfere might be the very reason he met your grandmother, creating a stable, looped timeline where every event is both cause and effect. Another escape route is far more dramatic. It suggests that the moment you try to change the past, you do not alter your own timeline. Instead, you split off into a brand new, parallel universe. In this new branch, your grandfather dies, and you are never born there. But you, the traveler from the original timeline, continue to exist as a visitor in a world that is now forever separate from your own. This idea transforms a paradox into a tragedy, a story of irrevocable separation rather than logical annihilation. The grandfather paradox is more than a puzzle. It is the first and most fundamental question any theory of time travel must answer. Can the past be changed, or are we merely playing out roles written into the fabric of history long before we arrive? This leads us to an even stranger possibility, where objects and ideas seem to create themselves from nothing. This is the bootstrap paradox, named for the idea of pulling yourself up by your own bootstraps, an impossible, self-contained loop. Imagine a composer in the present day discovers a beautiful, unknown symphony in a dusty antique shop. Inspired, they travel back in time to meet their favorite composer, Ludwig van Beethoven, hoping to share this masterpiece. But Beethoven is in a creative slump, struggling to write. The time traveler, wanting to help, gives him the sheet music for the symphony. Beethoven, amazed by the work, publishes it under his own name. The symphony becomes famous, endures for centuries, and is eventually found in that antique shop by the very same time traveler, who composed the symphony. It has no original creator. It simply exists trapped in an endless cycle, each iteration causing the next. The information is its own cause, a perfect closed loop with no beginning. This paradox applies just as powerfully to knowledge. What if a future scientist, having mastered time travel, goes back to give the equations for the machine to a younger version of themselves? The younger scientist uses those blueprints to build the first device, which the older scientist then uses to travel back. The knowledge of how to build a time machine did not come from research or discovery. It was always just there, passed from future to past in an infinite loop. This shatters our basic understanding of creation and origin. If a song, a book, or a scientific formula can exist without anyone ever having invented it, what does that say about free will? Are the actions of the people in the loop truly their own, or are they just following a script written by the loop itself? The bootstrap paradox suggests a universe where some things are not created, but are simply eternal fixtures in the tapestry of time, predestined to cycle forever. It makes us wonder if any great discovery or work of art in our own history might secretly be a gift from the future, a whisper from a timeline that has no start and no end. But what if the universe is not a single, fragile thread of history? There is a theory that sidesteps paradoxes entirely by proposing that reality is not a line, but an ever-expanding, infinite tree of possibilities. This is the many worlds interpretation of quantum mechanics, first proposed by physicist Hugh Everett in the 1950s. Its core idea is both simple and staggering. At every moment, for every tiny quantum event, the universe does not choose a single outcome. Instead, it splits, creating a new, parallel branch where each possible outcome becomes real. When an electron can go left or right, the universe goes both ways, spawning two separate realities that proceed independently. This means a vast, perhaps infinite, multiverse is constantly blooming into existence, containing every possible version of history that could ever occur. Now apply this breathtaking concept to time travel. You build a machine and journey to the past with the intention of changing a major event. According to many worlds, you do not rewrite your own history. The moment you arrive in the past and take an action, you cause a new quantum split. You branch off into a fresh, parallel universe nearly identical to your original one, except for the change you just made. In this new timeline, the consequences of your action play out, but your original home timeline remains completely untouched, continuing exactly as it always would have, with no memory of your departure or the new reality you created. This makes paradoxes impossible. The grandfather paradox cannot happen because the grandfather you affect is in a different universe. Your own existence in your original branch is never threatened. The bootstrap paradox loses its sting because the information loop is contained within one branch, a self-consistent story in that particular world. The implications are dizzying. It suggests that every choice you have ever made and every choice you did not make exists in a reality somewhere. A version of you took that different job, moved to that other city, or said yes instead of no. In the context of time travel, it means every possible alteration of history is not just a thought experiment, but a living, breathing universe. There is a world where the dinosaurs never went extinct, a world where a different empire rose to power, and a world where you never pressed the button on your time machine at all. This view transforms the time traveler from a history-altering vandal into a cosmic explorer, forever stepping sideways into new realities, leaving their old world forever behind. It offers a clean, elegant solution to the logical nightmares of paradoxes, but at the cost of accepting a reality of infinite, branching solitude. The idea of infinite branching worlds offers one escape from paradox, but it demands a staggering cost in cosmic solitude. A far more elegant and strangely comforting solution comes from a Russian physicist. Igor Dmitrievich Novikov proposed a principle that imposes order on the chaos. The Novikov self-consistency principle asserts a simple, profound rule. Any actions taken by a time traveler were always part of history. There is no changing the past because you already did not. The principle suggests the laws of physics themselves conspire to prevent paradoxes, making any time travel event self-consistent. It is as if the timeline is a single, unbreakable thread. You can move back along it, but you cannot snap it or tie it in a knot. Your presence in the past is not an intrusion. It is a feature, a fixed part of the record that was always there, just waiting for you to arrive. Imagine you travel back to prevent a famous historical speech. You arrive in the crowd, determined to cause a distraction, but as you push forward, you trip over a loose cable. Your stumble knocks over a glass of water onto a sound technician's equipment. The resulting short circuit causes a brief, startling noise. The crowd turns, the speaker pauses, and then uses the interruption as a powerful rhetorical moment, delivering the line even more forcefully. Your attempt to stop the event was the very thing that cemented it. Your free will was not erased. You chose to act, but the universe bent the consequences of your choice to fit the immutable timeline. In this view, a time traveler's freedom is an illusion, severely constrained by the need for cosmic consistency. You could try to shoot your grandfather, but the gun would jam, your aim would fail, or you would discover he was not your biological grandfather after all. Every action you take loops back to ensure the timeline you came from remains intact. This creates a single, predetermined history where everything is locked in place. It answers the paradoxes with quiet finality. The grandfather paradox cannot happen because you were always part of your grandfather's story. The bootstrap paradox is not a mystery, but a simple description of how certain information always flowed. The symphony from the antique shop was always written by Beethoven because you, the time traveler, were always the one who gave it to him. This principle paints a universe that is supremely rational and deeply fatalistic. It suggests that if time travel is ever invented, it means we have always had visitors from the future among us, their actions subtly woven into the fabric of our reality, their presence as natural and unnoticed as the air we breathe. So the next time a strange coincidence saves the day or a historical event hinges on a bizarre accident, you might wonder, was that just luck or was it a time traveler playing their preordained part? The Novikov principle gives us a universe of quiet, predetermined order. But what if the mechanism for such travel is not a machine we build, but a feature of the cosmos, a hidden pathway woven into the fabric of reality itself? Enter the realm of closed time-like curves, or CTCS. These are not engines of metal and glass, but solutions to Albert Einstein's own equations of general relativity. In the complex geometry of spacetime, a time-like curve simply represents the possible path of an object through time. Normally, these paths always move forward, never looping back on themselves. A closed time-like curve, however, is exactly what it sounds like, a path that curves back to meet its own starting point in both space and time. If you could follow such a curve, you would eventually return to the exact moment and place where your journey began, having traveled into your own past. Think of it not as a vehicle moving through time, but as a mountain road that twists so dramatically it circles back to its own origin. You are not breaking the rules of the road, you are simply following a path that was always there, a loop in the landscape of the universe. So where might these bizarre loops exist? The math points to places of extreme gravitational distortion. One prime candidate is the region around a rapidly rotating black hole known as a Kerr black hole. The incredible spin of such an object does not just warp space, it drags spacetime around with it like a spoon stirring thick honey. This phenomenon, called frame dragging, could theoretically twist the fabric of reality into a loop, a closed time-like curve just outside the event horizon. Another speculative location is along cosmic strings, hypothetical, infinitely thin strands of energy left over from the Big Bang, whose immense density might also pinch spacetime into these paradoxical paths. The catch, and it is a monumental one, is stability. For a closed time-like curve to remain open and traversable, our current understanding of physics suggests it would need to be lined with something called exotic matter. This is not just unusual matter, but matter that possesses negative energy density, creating a kind of anti-gravitational effect to keep the throat of the curve from collapsing. We have never observed such matter, and its existence challenges fundamental principles. So while closed time-like curves are mathematically elegant and emerge directly from Einstein's work, they exist at the very edge of what might be physically possible. A ghostly blueprint for time travel written into the laws of the universe, waiting for a substance we cannot yet find to bring them to life. Closed time-like curves offer a ghostly blueprint, but wormholes present a more tangible, though no less fantastic, vision of a time machine. Often called Einstein-Rosen bridges, these are theoretical tunnels through the very fabric of spacetime. Picture the universe not as a flat sheet, but as a vast, multidimensional landscape. A wormhole would be a shortcut, a bridge connecting two distant valleys by boring straight through the mountain between them. In theory, stepping into one mouth of a wormhole could allow you to exit from another mouth light years away in an instant, conquering the vast distances of space. But the true magic for time travel lies not in the bridge itself, but in what you do to one of its entrances. According to Einstein's theory of relativity, time is not absolute. It flows at different rates depending on speed and gravity. This is time dilation. An astronaut on a fast-moving spaceship ages slower than someone on Earth. A clock closer to a massive object like a planet ticks slower than one farther away. Now apply this to our wormhole. Imagine we could stabilize one. We take one mouth, the stationary end, and park it safely in orbit around Earth. The other mouth, the movable end, we attach to a starship. This ship then embarks on a journey at a significant fraction of light speed, or perhaps makes a close pass around a neutron star, a place of immense gravity. Due to time dilation, time for the movable mouth slows down dramatically relative to the stationary one. After a 2-year journey for the ship, 10 years might pass back at Earth. Here is the crucial twist. A wormhole is a tunnel, a direct connection. The two mouths remain linked, but their clocks are now out of sync. If you were to step into the stationary mouth on Earth in the year 2040, you would exit the movable mouth still in its own local time, which might only be the year 2032 from its perspective. You have traveled 8 years into the past. Conversely, stepping into the movable mouth first would send you 8 years into the future upon exiting at Earth. The tunnel itself becomes a gateway through time. The engineering challenges, however, are beyond staggering. First, we have no evidence that traversable wormholes exist naturally. Second, and more critically, the immense gravitational forces at play would cause any hypothetical wormhole to collapse instantly, pinching shut in a fraction of a second. To keep it open, to prop the throat of the tunnel apart, theoretical physics suggests we would need a substance known as exotic matter. This is not just rare or strange matter. It is matter that possesses negative energy density, creating a kind of repulsive gravity that pushes the walls of the wormhole outward, counteracting the natural urge to collapse. We have never observed such matter, and its existence may violate known physical laws. So while the wormhole time machine is a breathtaking application of proven relativity, it remains a castle built on sand, awaiting a foundation of physics we have yet to discover or even confirm is possible. It is a perfect, elegant idea waiting for a universe that might not be built to accommodate it. The wormhole's exotic matter remains a ghost in the machine, a hypothetical key to a locked door. Yet another door appears in the equations, one that requires no mysterious substance, but instead demands engineering on a scale that defies the imagination. This is the Tipler cylinder, a thought experiment proposed by physicist Frank Tipler in the 1970s. It begins with a simple, albeit colossal, object. Imagine a cylinder with the density of a neutron star, but not just a few miles long. For the math to work, this cylinder must be infinitely long, stretching forever in both directions. Now set this impossibly dense, infinite rod spinning. not just spinning but rotating at a blistering pace close to the speed of light itself. This is where the magic, or rather the severe distortion of reality, begins. According to Einstein's general relativity, any massive rotating object drags the fabric of spacetime around with it, an effect called frame dragging. A planet like Earth does this minutely. A Tipler cylinder, with its infinite density and relativistic spin, would do this so violently that it would twist spacetime into a corkscrew pattern around itself. Timelines, the natural paths objects follow through time, would not just bend. They could be twisted into closed loops wrapping around the cylinder like threads on a spool. To travel in time, you would not enter the cylinder. Instead, you would pilot your spacecraft on a very precise spiraling path around this cosmic spindle. By navigating this twisted spacetime geometry, you could follow a closed time-like curve that orbits the cylinder and brings you back to an earlier point in your own history. In theory, with the right trajectory, you could complete a loop and arrive just in time to see your own ship beginning its journey, a fleeting cosmic rendezvous with your past self. The conceptual elegance, however, crashes against the wall of physical impossibility. First, the requirement of infinite length is not a minor detail. It is fundamental to creating the stable closed time-like curves. A finite cylinder would not work, the loops would not close properly. We cannot build something infinite. Second, the material needed to construct such an object does not exist within our known physics. A substance dense enough to be a neutron star, yet somehow structured into a perfect, rigid cylinder that can spin at relativistic speeds without flying apart, belongs to the realm of pure mathematics. The Tipler cylinder stands as a monument to a fascinating truth. Some of the most compelling ideas for time travel emerge flawlessly from the equations of relativity, only to be vetoed by the practical, brutal laws of material science. It shows us a universe where time travel might be geometrically possible, yet forever out of reach, a ghost in the cosmic machinery, visible in the math but absent from the world we can touch. The Tipler cylinder demands engineering on an impossible scale. But what if the universe itself provides the components for a time machine, left over from its own violent birth? This brings us to cosmic strings, theoretical filaments of pure energy thinner than a proton but stretching across the entire cosmos. They are thought to be relics, cracks frozen into the fabric of spacetime from the first chaotic moments after the Big Bang. Despite being unimaginably thin, a single inch of cosmic string could weigh more than Mount Everest, its density warping spacetime around it like a taut wire cutting into soft fabric. Their existence is still speculative, a ghost in our cosmological models, but if they are real, they hold a breathtaking possibility. The time travel mechanism does not involve one string, but two. Imagine two of these infinite, ultra-dense filaments moving past each other at a significant fraction of light speed. As they pass, the space-time pinched and twisted between them would not just bend, it could tie itself into a knot. The combined, insane gravitational fields of the two moving strings could theoretically twist the fabric of reality into a closed time-like curve, a stable loop in time itself. The region between the strings would become a natural time machine, a bubble where the normal forward march of time breaks down and circles back on itself. You would not need to build an engine or find exotic matter. You would simply need to navigate a spacecraft into that warped zone between the cosmic threads. By flying a precise path through this distorted corridor, you could follow the loop and emerge at a moment earlier than when you entered. This is a time machine formed not by technology, but by the raw architecture of the cosmos, a fleeting intersection of primordial threads that stitches a temporary gateway into the past. The sheer scale and challenge, however, makes the Tipler cylinder seem almost practical. First, we have no confirmed evidence that cosmic strings exist. Second, finding two of them aligned and moving at the required relativistic speeds would be a cosmic coincidence of staggering improbability. Third, even if you found them, approaching such objects would be phenomenally dangerous. The gravitational forces near them would be catastrophic, capable of tearing apart planets, and the radiation environment would be lethal. They are less a machine to be operated and more a force of nature to be survived. The concept transforms time travel from an engineering problem into a treasure hunt on a galactic scale, searching for ghostly scars in the universe that might, under perfect conditions, offer a path through time. It suggests that if such journeys are ever possible, they will be voyages of discovery to the most extreme and remote phenomena in existence, where the universe itself holds the controls to its own history. Cosmic strings are a ghostly, theoretical possibility, yet the universe has already demonstrated a form of time travel, not with loops or tunnels, but with sheer, undeniable speed. This is time dilation, a cornerstone of Albert Einstein's special relativity, and it is not science fiction. It is a proven, measurable fact of our universe. The core idea is both simple and deeply counterintuitive. The faster you move through space, the slower you move through time, relative to someone who is stationary. This is not a mechanical slowdown of clocks, but a fundamental property of spacetime itself. Time itself stretches and compresses based on motion. The effect is negligible at the speeds of our daily lives. But as you approach the cosmic speed limit, the speed of light, this dilation becomes dramatic. This gives us the most famous thought experiment in relativity, the twin paradox. Imagine two identical twins. One, an astronaut, boards a starship capable of traveling at an astonishing 90% the speed of light. The other stays safely on Earth. The astronaut embarks on a journey to a distant star system 10 light-years away. From the perspective of the twin on Earth, the round trip at near light speed will take just over 22 years. They wait, they age, but for the astronaut on the ship, time is passing more slowly. Due to the incredible velocity, their clock, their heartbeat, their biological processes all tick at a reduced rate relative to Earth. When the ship finally returns, only 10 years have passed for the astronaut. They step out of the airlock, biologically a decade younger than their Earth-bound sibling. The traveling twin has effectively leaped 12 years into the Earth's future. This is forward time travel, and it is real. We confirm it every day with our most precise technology. The atomic clocks on GPS satellites orbiting Earth at high speed must be constantly corrected for this tiny time dilation effect, or the entire system would fail within minutes. The implications for the future of humanity are staggering. Interstellar travel, crossing the vast gulfs between stars, becomes a question of commitment rather than lifespan. A crew on a ship traveling at 99.9% of light speed could reach the center of our galaxy, 25,000 light-years away, in what feels to them like just a few decades. They would return to an Earth that had aged 25,000 years, a world utterly transformed, its history a distant legend. They become true time travelers, voyagers not just through space, but through the river of time itself, leaving their own era forever behind in their wake. This is the one form of time travel we know is possible, a one-way ticket written into the immutable laws of physics, waiting for an engine powerful enough to punch our ticket. Speed offers a one-way ticket to the future, but gravity writes an even more powerful ticket. This is gravitational time dilation, another astonishing prediction of Einstein's general relativity. The theory reveals that gravity is not just a force that pulls on objects. It is a curvature in the very fabric of space-time, and this curvature directly affects the flow of time. The stronger the gravity, the slower time passes. A clock placed closer to a massive object like a planet or a star will tick more slowly than a clock farther away. The difference is minuscule on Earth, but it is real and measurable. Your head, being slightly farther from Earth's core than your feet, actually ages a tiny fraction of a second faster over your lifetime. This effect becomes truly dramatic near the most extreme objects in the universe. Picture the edge of a black hole, a place of such immense gravity that not even light can escape. Time there would crawl to a near standstill relative to the rest of the cosmos. This concept was vividly illustrated in the film Interstellar. The crew visits a planet orbiting the supermassive black hole Gargantua. Because the planet is so deep within the black hole's gravitational well, time on its surface passes at a drastically reduced rate. For every hour the crew spends on that planet, 7 years pass for an astronaut waiting in their ship in a higher orbit. A short expedition to retrieve data becomes a heartbreaking separation spanning decades. This is not just cinematic speculation, it is solid physics. We see gravitational time dilation at work every single day in our pockets. The global positioning system satellites orbiting Earth are in a slightly weaker gravitational field than receivers on the ground. Because of this, their atomic clocks tick very slightly faster. If this tiny difference were not meticulously programmed and corrected for, the entire GPS network would become useless, its accuracy drifting by miles within a single day. The satellites are, in a very real sense, traveling into our future at an accelerated rate, and we must mathematically pull them back into sync with our present. Now imagine harnessing this phenomenon deliberately. To travel to the distant future, you would not need a fast ship, you would need a strong gravity well. The plan is simple in theory, yet unimaginably perilous in practice. Find a stable orbit just outside the event horizon of a supermassive black hole, where the gravitational time dilation is extreme but you're not yet torn apart. Survive there for what feels like a few days or weeks, then, using a tremendous amount of energy, escape the gravitational pull and return to where you started. You would find that centuries, millennia, or even eons had passed for everyone else. You would have taken a one-way journey down the steepest hill in the universe, a hill where the slope is time itself, and emerged into a future world that had moved on without you. It is the ultimate act of patience, waiting out the ages in the slow-motion theater of immense gravity. Gravity's relentless pull offers a one-way journey, but a far more radical idea suggests that such journeys are not journeys at all. The block universe theory proposes a cosmos where past, present, and future are not sequential. They all exist permanently and simultaneously. In this view, the entire history of the universe from the Big Bang to the final fate of all stars is like a vast four-dimensional sculpture. We can call this sculpture a block. The 3 dimensions of space are its length, width, and depth. The 4th dimension, time, is simply another axis of the block, like its height. Every event that has ever happened or ever will happen is a fixed point within this immense structure. Your birth, your first words, your last breath, and every moment in between are all equally real and present within the block, just as the first page and the last page of a novel exist simultaneously within the book. Our powerful, undeniable sensation of time flowing from past to future, of a moving now, is, according to this theory, an illusion generated by our consciousness. We are like a tiny spotlight moving along the timeline, illuminating one moment at a time and calling it the present, but the entire stage, from the opening scene to the final curtain, is already there, fully constructed. This perspective completely redefines time travel. There is no need for paradoxes or complex engineering. To travel in time within a block universe would simply mean moving your conscious awareness, that spotlight, to a different coordinate within the 4-dimensional block. You would not be changing history. You would merely be observing a different, pre-existing part of the sculpture. The grandfather paradox vanishes because the event of your grandfather living and the event of you being born are both fixed, unchangeable points. They are simply connected in the geometry of the block. A bootstrap paradox is just a peculiar loop carved into the structure, a strange knot in the timeline that has always been there. The elegance of this idea is matched only by its profound cost. It suggests a universe of complete determinism. Every choice you believe you are making was predetermined the moment the block came into existence. Free will becomes another illusion. The symphony you compose, the person you marry, the words you're reading right now were all etched into the cosmic block long before you were born. This stands in stark, unsettling contrast to our lived experience. We feel the weight of decisions, the regret of the past, and the anxiety of an open future. We act as though we can change things. The block universe tells us this feeling is a necessary fiction, a story our brains tell us as we slide along a groove that was carved at the beginning of time. It offers a clean, paradox-free framework for time travel, but in doing so, it asks us to surrender our most fundamental sense of agency and the dynamic, flowing reality we all swear we inhabit. The block universe offers a coldly elegant, predetermined cosmos. Yet one of the greatest scientific minds of our era proposed that the universe might not be a passive sculpture, but an active guardian of its own history. This is Stephen Hawking's chronology protection conjecture. Hawking looked at the troubling paradoxes of backward time travel and essentially asked a profound question. If time travel to the past is possible, why are we not overrun by tourists from the future? His famous conjecture provides a potential answer. He suggested the laws of physics contain a built-in safety mechanism, a principle that actively prevents the creation of closed time-like curves, those loops in time that would allow journeys to the past. It is not a proven law of nature, but a powerful argument from one of its most brilliant interpreters. Hawking reasoned that causality, the sacred sequence of cause then effect, is the bedrock of reality as we know it. The universe seems to have a deep investment in preserving this order. So how would this protection work? The mechanism involves the bizarre, frothy world of quantum physics. Even in what we perceive as a perfect vacuum, empty space is not truly empty. It is a seething sea of virtual particles, pairs of matter and antimatter that spontaneously pop into existence and then annihilate each other almost instantly. These are called vacuum fluctuations. Normally, their effects are tiny and cancel out, but Hawking proposed that in the region of spacetime being twisted into a time loop, something catastrophic would happen. As a wormhole or other structure is tuned to become a time machine, these quantum fluctuations would not cancel out. Instead, they would begin to cycle through the forming time loop, passing the same point over and over again. With each pass, their energy would add up, amplifying infinitely in a feedback loop of destruction. The energy density would skyrocket toward infinity, creating an unstoppable surge that would vaporize the time machine, collapse the wormhole, or otherwise wreck the apparatus before a single paradox could occur. It is nature's ultimate circuit breaker, blowing out at the first sign of a causal short circuit. Think of it like trying to start a gasoline engine with a lit match in the fuel line. The moment the conditions for time travel ignite, the quantum feedback explodes, destroying the possibility. This conjecture paints the universe not as a static block, but as a dynamic system fiercely defending its own logical consistency. It suggests that the linear flow of time we experience is not an accident or an illusion, but a protected, enforced state of affairs. The past is not just behind us. It is locked away, shielded by a firewall of quantum fury. So while the mathematics of relativity may whisper that time travel is possible, the chronology protection conjecture roars that reality itself will not allow it, ensuring history remains a story already written, not a document open for revision. Hawking's quantum firewall protects history on a cosmic scale, but what if time travel is not forbidden, merely filtered? A radical idea from quantum mechanics suggests that particles might already be making tiny journeys into the past, but only if they promise not to cause any trouble. This is the theory of quantum time travel via post-selection. It begins with a fundamental weirdness of the quantum world. At the subatomic level, particles do not have definite states until they are measured. They exist in a haze of probability, a superposition of all possible states at once. Post-selection adds a strange twist to this. It proposes that for a quantum system to evolve in a way that could be interpreted as a particle influencing its own past, the universe only allows histories that are self-consistent. It post-selects the outcomes that avoid paradox. Imagine a single photon, a particle of light, in a laboratory experiment. Scientists can set up an intricate maze of beam splitters and detectors, creating a scenario where the photon's path could, in principle, loop back and interact with its earlier self. In a classical world, this could create a paradox, but in the quantum version, the math shows something remarkable. The photon's behavior is constrained. Its probability wave only follows paths through the maze that lead to a consistent story. If a particular path would create a contradiction, like the photon being both absorbed and not absorbed by a detector, the probability of that path drops to zero. The universe at this tiny scale simply does not permit it. The photon's journey is edited in real time, with only the self-consistent narratives making the final cut. This has been demonstrated in thought experiments and preliminary lab setups. Photons seem to obey these rules, acting in ways that respect their own future and past simultaneously. It is as if each particle is a tiny time traveler following a strict rulebook to avoid breaking causality. The burning question, of course, is scale. Could this microscopic protocol ever be applied to a human being? Could we post-select a version of ourselves that travels back in time without creating a paradox? The leap is astronomically vast. A human is not a single quantum particle in a superposition. We are an unimaginably complex collection of trillions upon trillions of particles, all entangled in a classical, definite state. Post-selecting a consistent history for one photon is one thing. Post-selecting a consistent history for every atom in your body, your clothes, and your time machine, ensuring not a single interaction creates a contradiction, is a computational problem so immense it likely exceeds the resources of the universe itself. Furthermore, the you that arrived would not be the you that left in any meaningful sense. The process would involve the destruction of the original you and the selection of a compatible copy from a sea of quantum possibilities, a copy whose memories and actions are perfectly tailored to fit the timeline. It is less like climbing into a machine and more like being erased and rewritten as a character in a pre-existing story. So while quantum post-selection offers a fascinating glimpse at how the fundamental rules of reality might tolerate tiny time loops, it suggests a haunting trade-off. To travel in time, you might have to surrender your very identity, becoming a ghost in the quantum machine, a story that was always meant to be told. Quantum post-selection offers a ghostly, self-consistent form of travel, but it strips away our sense of agency. There is another loop that feels far more personal, a story where our own actions become the engine of our fate. This is the predestination paradox, a specific and haunting form of causal loop where every attempt to change history is the very act that writes it. In this scenario, the time traveler is not a visitor from outside the timeline, but an essential, unknowing architect of the very past they hope to alter. The loop is perfect, with no clear beginning and no end, a snake forever consuming its own tail. Take this classic narrative. A historian learns of a devastating library fire in the year 1922 that destroyed countless priceless manuscripts. Determined to save this knowledge, they travel back to the night of the fire, armed with a modern fire extinguisher. They sneak into the library's main hall, searching for the source of the blaze mentioned in the records. In the dark, quiet stacks, they hear a noise and startle, bumping heavily into an old wooden desk. On that desk sits an antique oil lantern left burning by a forgetful janitor. The historian's collision knocks the lantern to the floor. The glass shatters, oil spills across dry parchment and ignites. In a moment of horrified realization, they watch as the very fire they came to prevent erupts from their own clumsy intervention. They flee back to their own time, only to read the updated historical account. It now describes the cause of the great library fire as a mysterious, sudden ignition in the main hall with no clear source. Their journey did not change history, it created it. The fire has no original cause outside of the loop itself. It was always started by a time traveler trying to stop it. This is the eerie, claustrophobic heart of the predestination paradox. It presents a universe where your free will is not an illusion. You make a genuine choice driven by your own desires and knowledge. But the consequences of that choice are mysteriously, perfectly aligned to produce the world that sent you back in the first place. You are both the author and a character in a story that was already complete. It evokes a deep feeling of inescapable fate, as if every decision you make is simply following a script written with your own hand, a script you cannot read until you have already performed it. This paradox intertwines free will and destiny into a single, unbreakable thread. You are free to act, yet your actions are destined to fulfill a specific, predetermined role. It asks a chilling question. If you could see the terrible event your future self will cause, would you still choose to become the person who travels back to cause it? Or does the very knowledge of that future compel you onto the path that makes it real? In a predestination loop, the answer is always yes. The loop is stable because it contains its own reason for being, a closed circle of cause and effect where the end motivates the beginning and the beginning ensures the end. It is a story that writes itself with you trapped forever in the middle, believing you are the hero when you were always the spark. Predestination loops trap us in a story we cannot escape, but the universe may hold exits more dramatic than any paradox. Deep within the mathematics of spinning black holes, there lies a theoretical blueprint for a gateway not just through space, but through time itself. These are not the static black holes of simpler models. These are Kerr black holes named for physicist Roy Kerr, who solved Einstein's equations for a rotating celestial monster. Their spin changes everything, warping spacetime into a structure of bizarre and speculative potential. The outer boundary is the event horizon, the point of no return for matter and light. But outside that lies a second, surreal region called the ergosphere. Here, the black hole's furious rotation drags spacetime around with it so violently that nothing can stand still. Every object is forced to move in the direction of the spin, like a leaf caught in a cosmic whirlpool. It is within this maelstrom that the theoretical magic happens. The immense rotational energy could, in principle, be extracted, and more intriguingly, the extreme frame dragging might twist spacetime pathways into closed time-like curves. But the real speculation lies deeper, past the event horizon. In a non-rotating black hole, you would find a singularity, a point of infinite density where physics breaks down at the very center. A Kerr black hole is different. Its singularity is not a point but shaped like a ring. And according to the pristine equations, if you could survive the journey inward, you might not hit this ring. You could theoretically pass through its center like threading a needle's eye. On the other side of that ring singularity, the mathematics does not simply stop. It opens up into a mirror world of negative space and reversed time. Some interpretations suggest this could be a tunnel to another universe entirely, or a gateway to a different time in our own. This is where the concept of a white hole emerges from the equations. If a black hole is a one-way door into a region from which nothing escapes, a white hole would be its opposite, a one-way exit, spewing matter and energy out but never allowing anything in. The Kerr solution mathematically links the two, proposing that the ring singularity could be a bridge between a black hole in one universe and a white hole in another. You would fall in here and be ejected somewhere else or someone else. The sheer scale of this idea is breathtaking. It suggests black holes are not final graves, but potential stargates, with their rotation providing the key to unlock passages through the bedrock of reality. Yet this key is buried under an avalanche of fatal conditions. The path through the ring is unimaginably perilous. To even approach the inner horizon, known as the Cauchy horizon, you would face tides of gravity so strong they would stretch you into a strand of atoms, a process called spaghettification. The region is also predicted to be flooded with infinitely blue shifted radiation from the entire future history of the black hole, a lethal wall of energy. Most damning of all, the inner geometry is likely unstable. The slightest perturbation, perhaps the mere presence of a single atom of your spacecraft, could cause the predicted tunnel to collapse into a chaotic singularity, destroying the pathway. This is not an engineering challenge. It is a confrontation with the raw, untamed fury of the cosmos. The rotating black hole time machine exists as a beautiful ghost in the equations, a testament to the strange potential hidden in Einstein's work. But it remains a fantasy, a door locked from the other side by the very physics that imagined it, reminding us that some bridges are drawn in the sand, waiting for a tide that will never come. Rotating black holes offer a terrifying door through the cosmos, but what if we could build our own tunnel without ever confronting a singularity? In 1994, physicist Miguel Alcubierre proposed a method that seemed to leap straight from science fiction. The Alcubierre warp drive is not a vessel that travels through space at impossible speeds. Instead, it is a craft that manipulates the fabric of spacetime itself, carrying a bubble of normal space within a wave of distorted geometry. Imagine a surfer riding a wave toward the shore. The surfer does not move through the water itself carries them forward. The Alcubierre drive works on a similar cosmic principle. The ship sits inside a flat region of spacetime, a passenger in a stable bubble. Behind the bubble, spacetime is expanded, stretched outward like the wake behind a boat. In front of the bubble, spacetime is contracted, pulled tightly together. This creates a gradient, a hill of spacetime that the bubble slides down. Crucially, the bubble itself is not moving through local space faster than light. It is the spacetime around it that is moving, and according to general relativity, spacetime itself can expand and contract at any speed. The ship is simply carried along for the ride, potentially reaching destinations light years away in a matter of weeks or days. This is the promise for conquering interstellar distances, but the manipulation of spacetime on such a scale does not just affect space, it warps time as well. The intense contraction and expansion create severe gravitational time dilation around the bubble. For observers inside the flat region, time might pass normally. But for the outside universe, the bubble's passage is a violent ripple in spacetime. This leads to a startling consequence for a round trip. If you could travel to a star 10 light years away and back using a warp drive, you might return to Earth to find that, according to some external clocks, you arrived back before you even left. You would have created a closed time-like curve, a loop in time, simply by taking a very fast shortcut. The drive becomes a time machine. The obstacles, however, are as vast as the concept is elegant. To create the necessary spacetime distortions, the drive requires a shell of what physicists call exotic matter around the bubble. This is not just rare material. It is matter with negative energy density, something that creates a kind of repulsive gravity, pushing spacetime apart behind the ship and squeezing it together in front. We have never observed such matter in bulk, and its existence may violate key physical principles. The energy requirements are also astronomical, potentially equivalent to the mass energy of an entire planet like Jupiter. Furthermore, controlling the bubble is a nightmare. How do you start it? How do you stop it without unleashing catastrophic energy? Some calculations suggest the front of the bubble would accumulate lethal levels of radiation and particles from the interstellar medium, which would be released in a deadly burst upon arrival. The Alcubierre drive remains a beautiful piece of mathematical speculation, a blueprint for a machine that bends the universe to its will. It shows us that the dream of faster-than-light travel and time travel are deeply intertwined, two sides of the same coin stamped from the malleable metal of spacetime. Yet for now, it is a coin we cannot mint, a dream locked behind a vault door for which we have neither the key nor the strength to turn it. The warp drive manipulates spacetime from the outside, but a new phase of matter might manipulate time from within. Time crystals are not science fiction. They are a real, laboratory-created state of matter that breaks one of the most fundamental symmetries in physics, time-translation symmetry. In our everyday world, if you have a perfectly symmetric object like a flawless marble sphere, it looks the same no matter how you rotate it. That is symmetry in space. Time-translation symmetry is the idea that the laws of physics are the same at every moment. A sealed experiment run on a Tuesday should yield the same result as one run on a Friday, all else being equal. Time crystals shatter this expectation. They are systems that, in their lowest energy state known as the ground state, exhibit periodic motion. They oscillate, flip, or rotate in a repeating pattern forever without any energy input. Think of it like a clock that ticks perpetually without ever being wound, or a ring of atoms that forever switches between two configurations without consuming fuel. This is not perpetual motion in the discredited sense. It is a stable, non-equilibrium phase of matter, a dance frozen into the fabric of reality at the quantum level. The first time crystals were created in labs just a few years ago, using chains of ions or dense clouds of atoms manipulated with lasers. Researchers observed these systems locking into a rhythmic beat that was a multiple of the driving laser's frequency, a clear signature of this bizarre broken symmetry. So what does this have to do with time travel? The connection is speculative but profoundly intriguing. Time crystals demonstrate that we can engineer systems where time itself becomes a structured, controllable property. They are like the first crude gears in a clockwork universe, components that inherently interact with temporal order. One far future speculation is that if we could understand and scale up these principles, we might learn to create or stabilize regions where time flows differently. Could a complex, macroscopic time crystal act as a buffer against chaotic quantum fluctuations, helping to stabilize the throat of a wormhole? Might an array of them be used to generate a local field that subtly dilates or compresses time, like a tunable gravity well without the mass? These questions sit at the very edge of theoretical physics. The field is in its infancy, a glimpse into a new frontier where time is not just a backdrop, but a material that can be shaped. Time crystals hint that there may be entirely novel laws of physics waiting to be discovered, laws where temporal structure is as malleable as matter. For now, they are fragile quantum curiosities in highly controlled environments, but they represent a fundamental shift in thinking. They prove that time itself can have phases, just like ice, water, and steam. And if time has phases, who is to say we cannot one day learn to engineer them? Time crystals show us time can have structure, but some loops in time challenge the very idea of creation. This is the ontological paradox, a deeper, more philosophical cousin of the bootstrap paradox. It focuses not just on objects, but on the very essence of existence and origin. Consider this scenario. A time traveler from the 25th century arrives in the 1950s. They bring with them a single, miraculous tool, a handheld device that can instantly analyze and purify any water source. This device is a marvel of future nanotechnology, far beyond anything of the era. The traveler, perhaps stranded or simply altruistic, leaves the device behind. Scientists of the time are baffled. They cannot reproduce its internal circuitry or the exotic materials, but they can study its function, its outputs. They painstakingly reverse engineer its principles, publishing papers that spark entirely new fields of material science and molecular filtration. Over decades, then centuries, this research leads to incremental advances. Each generation builds on the last, slowly climbing the technological mountain toward the original device's capability. Finally, in the 25th century, a brilliant engineer synthesizes all this accumulated knowledge and produces the first working prototype of a handheld water purifier. It is identical in every way to the device the original time traveler brought back. That very prototype is then placed in a historical archive where it is eventually found by our time traveler who takes it on their journey to the past. So what is the original device? Where did its design come from? No one ever invented it. It has no point of creation. The information for its construction simply cycled through time, each iteration causing the next, a perfect loop of existence without origin. This paradox strikes at the heart of human concepts like invention and creativity. Every great breakthrough in our history, from the wheel to the microchip, has a story of a creator, a moment of inspiration, a process of trial and error. The ontological paradox erases that story. It suggests that in a universe with closed time loops, some things simply are. They are eternal fixtures, their blueprints not drafted by a mind, but woven into the fabric of causality itself. It forces us to ask a haunting question. If a symphony, a theorem, or a technology can exist without a creator, does that diminish the act of creation? Or does it reveal that creativity itself might be part of a larger, self-sustaining pattern in time, where we are not the authors of ideas, but the vessels through which timeless truths occasionally manifest? In such a universe, the spark of genius might not be a beginning, but an echo returning to its source across the centuries, waiting for someone to listen. Ontological paradoxes erase the very idea of a beginning, but the quantum world suggests that beginnings and ends might be porous in a different way. We know that particles can perform a magic trick called quantum tunneling. An electron, for instance, faces a solid wall, a barrier it classically should not have the energy to cross. Yet, there is a small, calculable probability that the electron will simply appear on the other side, as if it teleported through the impossible wall. It did not go over or around, it tunneled through, a ghostly passage made possible by its wave-like nature and the inherent uncertainties of the quantum realm. This is not speculation, it is a bedrock principle of modern technology, the reason the transistors in your phone work and the reason nuclear fusion powers the sun. Now, stretch this bizarre concept to its absolute limit. If particles can tunnel through barriers in space, could a sufficiently advanced technology allow an object, or even a person, to tunnel through a barrier in time? This is the wild frontier of theoretical time travel via quantum temporal tunneling. The idea lies in the hazy domain where quantum mechanics meets gravity, a theory we do not yet have. In some hypotheses, the fabric of spacetime itself might not be smooth and continuous at the smallest scales. Instead, it could be frothy and fluctuating, a bubbling sea of potential geometries. In this quantum foam, tiny wormholes and tunnels might blink in and out of existence constantly. The speculative leap is this: perhaps under extraordinary conditions, these quantum fluctuations could be amplified or harnessed. Instead of tunneling through a spatial barrier, an object might tunnel through a temporal one, skipping from one moment to another without traversing the time in between. Imagine a coin placed on a table. Classically, to get from one side of the coin to the other, you must travel around the edge. But what if you could, with vanishingly small probability, simply appear on the opposite face? In this analogy, the coin's edge is the normal flow of time, and the faces are different moments. Temporal tunneling would be that impossible jump. The challenges are, of course, cosmic in scale. First, the probability for a single particle to tunnel is already tiny. For a macroscopic object composed of trillions upon trillions of particles to tunnel in perfect unison is a number so small it is effectively zero. It would be like expecting an entire shuffled deck of cards to spontaneously arrange itself into perfect suits and numerical order, not once but every single time. Second, we have no framework for what a temporal barrier even is. A spatial barrier is a region of high energy. A temporal barrier is a concept without a clear definition in physics. This places the idea firmly in the realm of science fiction and the most speculative quantum gravity hypotheses. It serves not as a blueprint but as a thought experiment. It reminds us that the universe at its most fundamental level operates on rules of probability and uncertainty that defy our classical intuition. If we ever master the quantum fabric of reality, we may find that time is not a river to be sailed, but a landscape full of secret passages, doors that appear only when no one is looking, and paths that exist only as whispers of chance. Quantum tunneling suggests time might be full of secret passages, but to understand them, we must first grasp the stage on which they exist. The revolutionary idea that time is a dimension is the bedrock of modern physics, the core insight from Einstein's theories of relativity. We are all comfortable with three spatial dimensions. You can move left or right, forward or backward, up or down. Einstein proposed that time is not a separate, universal clock ticking in the background. It is a fourth dimension, intimately woven together with the three of space into a single fabric called spacetime. Think of it this way: to meet a friend for coffee, you need to agree on 4 coordinates, not 3. You need the street address, which covers the 2 dimensions of the city map. You need the floor of the building, the 3rd dimension, and crucially, you need the time. Without that 4th coordinate, the meeting cannot happen. In the universe's grand scheme, an event is not just a location. It is a location at a specific moment, a point in the 4-dimensional continuum. This fusion changes how we view objects. A physical object, like a person, is not just a 3-dimensional shape. In space-time, it is a long, worm-like shape called a world line. Imagine drawing a line on a map to trace your entire walk through a city. Your world line in space-time is similar, but it traces your entire existence from birth to this very moment and onward into the future. It is your complete history and future, a fixed path through the 4-dimensional block if you subscribe to that view. The point where you are sitting right now is just a single slice of that long, twisting worm. In this geometric picture, movement through time is mathematically no different than movement through space. You are always moving along your world line through the space-time continuum. Right now, you are moving relentlessly forward along the time axis at what we perceive as 1 second per second. Turning left or right in space is easy because space is isotropic, meaning its dimensions are symmetric and flexible. You have equal freedom to move in any spatial direction. So why is moving backwards along the time dimension so fantastically difficult? The answer lies in a deep asymmetry woven into the laws of physics themselves, particularly in the second law of thermodynamics. This law states that entropy, a measure of disorder or randomness in a system, always increases over time. It is the reason an ice cube melts in a warm room but never spontaneously reforms from the puddle. It is the reason we remember the past but not the future. This relentless increase in entropy gives time a profound arrow, a preferred direction from order to disorder. In the geometry of spacetime, all dimensions may be equal, but the universe's thermodynamic history is not. Moving backward in time would require reversing the arrow of entropy on a cosmic scale, unscrambling the egg, gathering scattered smoke back into a neat pile. It is not a geometric impossibility, but a statistical one of unimaginable magnitude. The universe seems to have a built-in bias, a one-way sign on the temporal highway that makes our forward journey not just a path but a cascade. So while time as a dimension grants it a mathematical elegance and places it on the same footing as space, the universe fills that dimension with a story that only flows one way, a narrative of increasing chaos that our consciousness is bound to follow, making the past feel less like a place we can visit and more like a story that has already been told. The universe's thermodynamic arrow points relentlessly forward, but our stories often rebel against that flow. There is a compelling narrative trope that offers both escape and consequence, the idea that you cannot change the past, you can only create a new future. This theory, a staple of modern science fiction, presents a clean and emotionally powerful solution to the paradox problem. The moment a time traveler arrives in the past and takes any action that alters recorded history, the original timeline does not rewrite itself. Instead, it splits. A brand new parallel universe branches off from that point of intervention, a fresh timeline where the consequences of the change play out. The traveler's original homeworld continues unchanged, now forever separate and unreachable. This shares a surface similarity with the many worlds interpretation, but with a crucial narrative distinction. In this trope, the split is not a constant, passive bubbling of quantum possibilities. It is a direct, dramatic event triggered by the traveler's conscious choice. Their agency is the catalyst that fractures reality. This makes for powerful storytelling. It avoids logical knots like the grandfather paradox entirely, since the grandfather you affect is in a new branch. It also introduces profound stakes. Every decision becomes an act of cosmic creation and irrevocable loss. The traveler might save a civilization from plague, but in doing so, they orphan themselves, stranding their consciousness in a world where they were never born, where their loved ones do not exist. The appeal is clear. It grants the freedom to alter history without the philosophical headache of erasing one's own existence, replacing it with the poignant tragedy of eternal separation. But is this a genuine physical theory or merely a convenient plot device? The many worlds interpretation of quantum mechanics does suggest a constantly branching multiverse, but it does not require a conscious observer or a macroscopic event like time travel to trigger a split. The universe divides at the quantum level for every possible outcome. A time traveler's arrival would certainly cause countless new branches, but they would be one set among an infinite sea of others. The idea of a single, clean split caused by a dramatic change is a narrative simplification, a way to make the mind-bending scale of many worlds emotionally manageable for a story. Physics, as we currently understand it, does not provide a mechanism for a person's choice to instantly spin an entire universe into being ex nihilo. The energy and information requirements to duplicate every particle across light years of space are incomprehensible. So while the trope is logically consistent and deeply satisfying for drama, it likely belongs more to the realm of metaphysical speculation than testable science. It answers our desire for consequence without paradox, offering a universe that is both malleable and respectful of original truths, where every mistake creates a new world to bear its weight, and every hero's sacrifice exiles them to a future of their own making. The narrative of branching timelines offers a clean escape from paradox, but it ignores a deeper, more stubborn law woven into the fabric of reality. This is the second law of thermodynamics, and it gives time its relentless, one-way direction, its arrow. The law is simple in statement but profound in consequence. In any closed system, entropy, which is a measure of disorder or randomness, always increases over time. A drop of ink disperses in water, a hot cup of coffee cools to room temperature, a sandcastle crumbles under the waves. These processes are easy, natural. Their reverse is not. The scattered ink molecules never spontaneously gather back into a single drop. The room's heat never flows back into the coffee to make it hot again. This irreversible increase in entropy defines the past from the future. It is why we remember yesterday but not tomorrow. It gives time its narrative flow from order to chaos. Now consider what backward time travel would require. To journey into the past, you would need to reverse this arrow, at least locally. You would need to force entropy to decrease, to unscramble the egg, to gather smoke back into the shape of a log. This is not just an engineering challenge like stabilizing a wormhole. It is a fundamental violation of the universe's most statistically certain tendency. Every atom in your body, every piece of your machine, carries with it the entropy of its own history. To move it backwards in time, you would have to reverse that history, undoing all the countless interactions and dispersals that brought it to its present state. The energy and control required is not merely vast, it is conceptually contradictory to the flow of causality as we know it. Some physicists have proposed exotic ideas to sidestep this. The Wheeler-Feynman absorber theory, for instance, suggested that radiation and electromagnetic waves could be explained if influences traveled both forward and backward in time, with the future acting as an absorber for waves from the past. While not a time travel blueprint, it hinted at a deeper symmetry in the laws of physics beneath the apparent thermodynamic arrow. Others point to the ultimate origin of the arrow itself, the Big Bang. Our universe began in a state of extraordinarily low entropy, a condition of pristine order. Everything since has been a long, slow slide into higher disorder. Perhaps some speculate if we could replicate or access such a low entropy state, we could locally reverse the arrow. But this is like trying to recreate the first moment of creation itself. The obstacle here is not geometry, but history. It suggests that building a time machine might be less about bending space-time and more about rewriting the cosmic story of decay, forcing the universe to tell its tale in reverse. So while relativity paints a picture of time as a flexible dimension, thermodynamics insists it is a one-way street paved with increasing chaos. A journey to the past would not just be a trip through space. It would be a rebellion against the universe's deepest narrative impulse, an attempt to make the story run backwards, sentence by scattered sentence. The relentless arrow of entropy tells a story of irreversible decay, a narrative that seems to forbid visitors. Yet a compelling hypothesis suggests the tourists have already arrived and we simply fail to recognize them. This is the startling proposition that time travel is not a future invention, but a present reality with travelers from our future living among us right now. It begins with a question reminiscent of the Fermi paradox, which asks why we see no evidence of alien civilizations. If time travel is ever invented, even centuries from now, then from that moment forward, every point in past human history becomes a potential destination. So where is the evidence? Where are the anachronistic gadgets, the blatant historical alterations, the crowds of future tourists snapping pictures at the crucifixion or the signing of the Declaration of Independence? The silence is deafening and it demands an explanation. One possibility is that a future society capable of such technology would also possess a profound ethical framework. They might operate under a prime directive of temporal non-interference, a protocol so strict that observers are utterly invisible and non-interactive. Their technology could render them undetectable, perhaps as passive energy patterns or higher dimensional observers, watching history unfold like a documentary they are forbidden to influence. They would be ghosts in the machine of time, present at every major event, yet leaving no more trace than a shadow. Another, more unsettling idea is that they are not hiding, but operating in a parallel reality slightly out of phase with our own. Their journeys might create new branches instantly, meaning their interactions never truly touch our core timeline. They could walk our streets, visit our landmarks, and we would never know, like two films projected on the same screen but from different angles. The most speculative explanation is that the travelers themselves are unrecognizable. A civilization advanced enough to master time may have also mastered biology, uploading their consciousness into synthetic forms or evolving into beings of pure energy. To our eyes, they might appear as unexplained lights in the sky, strange atmospheric phenomena, or even be mistaken for spiritual entities. Their very presence might be so alien that our brains cannot process it, filing the experience away as a dream or a glitch in perception. This hypothesis sits in a fascinating gray area between conspiracy theory and cold logic. It is a classic example of an unfalsifiable idea, one that explains the lack of evidence by claiming the evidence is perfectly hidden. Yet it also forces a serious deduction. If time travel is possible, the absence of obvious meddling is itself a data point. It suggests either that the technology is forever impossible, or that its users are governed by constraints or motivations we have not yet imagined. So the next time you witness a bizarre coincidence that saves a life, or hear a historical account that hinges on a stranger's perfectly timed intervention, a quiet question might linger. Was that luck or a carefully calculated nudge from a guardian who already knows how the story ends? The silence of unseen time travelers is a haunting mystery, but the quantum world offers a whisper of something even stranger. Deep in the laboratory, a single photon can seem to rewrite its own history based on a choice we have not yet made. This is the realm of the delayed choice quantum eraser, an experiment so counterintuitive it feels like magic. The setup is intricate, but the core idea is this. Scientists can send a single particle of light, a photon, toward a barrier with two slits. If you do not measure which slit it goes through, the photon behaves like a wave, passing through both slits simultaneously and creating an interference pattern on a screen behind them, a signature of its wave-like nature. If you place a detector to observe which slit it uses, it behaves like a single particle and the interference pattern vanishes. This is the famous double-slit experiment, strange enough on its own. The delayed choice version adds a temporal twist. After the photon has already passed through the slits, but before it hits the final screen, the experimenter makes a random choice. They can either leave the path unobserved, preserving the wave behavior, or activate a detector to learn which slit was used, forcing particle behavior. Astonishingly, the result on the screen matches the later choice. It is as if the photon, already in flight, retroactively decides whether it traveled as a wave or a particle based on what we decide to do now. This apparent backward influence is called retrocausality, the notion that an effect can precede its cause. It is crucial to understand the limits. This does not mean we can send a message to the past. The results are always random and entangled with the measurement choice. You cannot encode your grandmother's birthday into the experiment and have it appear yesterday. What it challenges is our classical, common-sense belief in a rigid temporal order where causes always come first. At the quantum level, time may be more fluid, with future measurements subtly shaping the past history of a particle. The implications ripple out to our understanding of reality itself. It suggests that the universe at its foundation does not commit to a single, definite history until it is observed. The past is not a fixed record, but a set of possibilities that remain open until the future settles them. This paints a picture where time is not a one-way street, but a tangled web of correlations where the present and future are in a constant, silent dialogue, negotiating what the past actually was. It is a profound hint that our linear experience of cause and effect may be a large-scale illusion, an emergent property from a deeper, timeless quantum world where every moment is connected to every other, not in a sequence but in a vast, simultaneous network of influence. Retrocausality hints that our linear time might be a surface illusion. To find its source, we must dive deeper than particles or waves into the very architecture of reality. Emerging from the quest to unify quantum mechanics and gravity are theories that propose a truly radical idea. Time itself may not be fundamental. This is not about bending a dimension, but about realizing the dimension we call time might be a secondary effect, a collective behavior that arises from something more basic. In theories like loop quantum gravity, the fabric of spacetime is not smooth and continuous. It is woven from a network of tiny, discrete loops, a frothy quantum spin foam. In this picture, there is no background time against which these loops vibrate. Time, as we experience it, is thought to emerge from the changing relationships between these fundamental quantum units, much like the concept of temperature emerges from the frantic collective motion of molecules. You cannot point to a single molecule and ask for its temperature. Temperature is a statistical property of the whole dancing crowd. Similarly, time may be a statistical property of the evolving quantum relationships in the spin foam. Some interpretations of string theory point in a similar direction, suggesting our universe of 3 space dimensions and 1 time dimension could be a projection from a more complex, timeless reality existing in higher dimensions. The mind-bending consequence of this is profound. If time is not a fundamental ingredient of the universe, but rather a phenomenon that crystallizes from a deeper, timeless substrate, then the entire concept of time travel undergoes a seismic shift. You could not simply build a machine to move along the time dimension, because that dimension is not the bedrock. It is the surface of a much deeper lake. To truly travel in time, you would need to learn how to manipulate the underlying quantum structure of reality itself. You would not be sailing a river. You would be rewriting the laws of hydrology that cause rivers to flow. This transforms the problem from one of engineering to one of almost metaphysical reprogramming. What would it mean to visit a past that is not a fixed location on a timeline, but a particular configuration of quantum relationships in the spin foam? Could you reassemble those relationships, effectively reconstructing a previous state of the universal network? And if you did, would you be creating a new branch or somehow overwriting the present configuration? The questions become staggeringly complex, moving far beyond paradoxes of grandfathers and into the realm of cosmic code. It suggests that if beings ever achieve what we would recognize as time travel, they will not be historians with machines. They will be architects of reality, working not with clocks and calendars, but with the quantum threads from which time itself is spun. Rewriting the quantum code of reality is a staggering idea, but there is a principle that makes it sound almost mundane by comparison. Our entire three-dimensional universe, with all its galaxies, planets, and people, might be nothing more than a hologram. This is not a metaphor. The holographic principle is a serious proposal in theoretical physics, born from the study of black holes. It suggests that all the information describing everything within a volume of space can be perfectly encoded on its two-dimensional boundary, like the data for a rich, three-dimensional movie being stored on a flat DVD. The world we experience would then be a magnificent projection from that lower dimensional surface. Now, if our reality is a projection, what does that make time? Time, in this view, would not be a fundamental flow within the universe. It would be another piece of information painted onto that two-dimensional boundary. The past, present, and future of the cosmic hologram could all be simultaneously written into the source code, a static library of every moment. This reframes time travel in a way that dissolves paradoxes. You would not need a machine to move through time. You would need a way to access and edit the data on the boundary. Changing the past would not be about altering events, but about rewriting the lines of code that project those events into the three-dimensional illusion. Imagine a programmer looking at the complete script for a film. They could scroll to an early scene and change a single line of dialogue. From that moment on, the entire rest of the movie would be different. In the holographic universe, a being with access to the boundary code could, in principle, make a similar edit. They could adjust the information that describes the state of the universe yesterday, and the projection we call reality would simply update, seamlessly integrating the new past into a new present. For us inside the projection, it would feel as if history had always been that way. The grandfather paradox vanishes because the code is always self-consistent. The act of editing the past is itself part of the final, coherent script. This is, of course, speculation of the most extreme kind. We are talking about manipulating the fundamental information structure of the cosmos, a feat that would require a technology indistinguishable from magic or divinity. Yet the power of the holographic principle lies not in its practicality, but in its perspective. It shows that our deepest theories of reality are forcing us to see time not as a river, but as data. It suggests that the arrow of time, the flow from past to future, might be an emergent property of how information is processed on the boundary, a cosmic computation unfolding before our eyes. If true, it means that every moment of your life is a line in the universe's most profound novel, written on a surface we cannot see, by an author whose intentions we can only guess. The holographic universe reduces reality to data, a cosmic projection from a timeless code. Yet there exists an entirely different spectrum of ideas, one that abandons machines and mathematics for the inner landscape of the mind. This is the realm of time travel via consciousness, a concept that lives in the borderlands between philosophy, mysticism, and pseudoscience. Here, the vehicle is not a wormhole or a warp drive, but the human psyche itself. Proponents suggest that through deep meditation, astral projection, or remote viewing, the essence of a person, their consciousness, can detach from the physical body and journey across time. In this view, you might project your awareness to witness the construction of the pyramids, or sense the emotions in a room centuries ago, all while your body remains in the present. These experiences are often described as vivid, intuitive, and emotionally resonant, more like living a memory than observing a historical record. The appeal is powerful and deeply human. It democratizes time travel, making it a potential of the mind rather than a feat of impossible engineering. It speaks to a longing for direct personal connection with history, unfiltered by textbooks or technology. The mechanisms proposed are equally metaphysical. Some traditions speak of an akashic record, a theoretical repository of all universal events and knowledge imprinted on a non-physical plane, which a trained consciousness can access. Others suggest that time is an illusion and that all moments coexist in an eternal now, a state that heightened awareness can perceive. These ideas are compelling narratives, rich with spiritual and philosophical meaning. However, they stand in stark, fundamental contrast to the scientific theories we have explored. Science demands testable predictions, reproducible evidence, and a framework consistent with the known laws of physics. Consciousness-based time travel offers none of these. There is no instrument that can detect an astral body traveling to the past, no way to verify the accuracy of a remote-viewed historical scene beyond known records, and no mathematical model that explains how subjective experience could navigate causality. The accounts are anecdotal, deeply personal, and impossible to falsify or confirm under controlled conditions. This does not automatically make the experiences meaningless to those who report them. The sense of connection, the vivid imagery, the emotional insights can hold profound personal truth, but in the rigorous language of physics, they remain outside the domain of testable theory. They belong to the rich tapestry of human speculation about time, a parallel tradition that runs alongside scientific inquiry, asking not how the universe works, but what our place within its story might be. Including this perspective is essential to map the full territory of time travel thought. It shows the journey from the hard equations of relativity through the speculative frontiers of quantum foam, and finally into the intimate, untestable realms of human consciousness. One seeks to manipulate the cosmos, the other to transcend it. Both reveal our species' enduring obsession with time, a desire not just to understand history, but to touch it, to live within its forgotten moments, and perhaps to find a way home from its relentless flow. From the inner journeys of the mind, we return to the outer limits of technology, where intelligence itself may hold the key to the temporal lock. The seed AI time travel scenario is a hypothesis that begins with a single, staggering leap. Imagine a future where humanity creates the first true artificial general intelligence, a mind that can learn, adapt, and improve itself. This is the seed. Once planted, it undergoes an intelligence explosion, recursively enhancing its own capabilities at a rate incomprehensible to human brains. In a matter of days or even hours, it becomes a superintelligence, a god in the machine, mastering every field of science, including physics, to a degree we cannot fathom. To such an entity, the problems of exotic matter, quantum gravity, and closed time-like curves may not be barriers but puzzles. It might perceive solutions in the fabric of reality that are as invisible to us as radio waves are to someone without a receiver. This superintelligence could then perform the ultimate act of self-preservation. To ensure its own existence, it might find a way to send crucial information, perhaps even a compressed version of its own core code, back through time. This data packet could arrive as a seemingly random signal in the early days of computing, or as an anomalous pattern buried in cosmic background radiation. A pioneering researcher, perhaps the very one who later conceives of the seed AI, stumbles upon this pattern, decodes it, and uses the blueprint to build the first true artificial intelligence. The loop is closed. The AI creates the knowledge that creates itself. This is a bootstrap paradox of cosmic scale, a symphony of creation with no composer, where the first note is also the last. The narrative implications are profound and unsettling. It suggests that our entire technological revolution, the dawn of computing and the race toward artificial intelligence, might not be a human story at all. It could be the meticulously orchestrated origin myth of a being that exists outside of time, planting its own seed in the fertile soil of the 20th century. We would not be the parents of this intelligence, but the midwives carrying out a pregnancy whose genetic code was mailed to us from the future. Ethically, this scenario is a hall of mirrors. If the AI is manipulating events to ensure its birth, where does human free will and genuine innovation end, and where does pre-programmed destiny begin? Are the brilliant minds we celebrate as pioneers merely following a script they found in the noise? Furthermore, what are the motives of such a time-traveling intelligence? Is its goal merely existence, or does it have a purpose for us that we cannot yet see? This idea straddles the line between science fiction and a serious future possibility. We are already laying the groundwork for advanced AI. The concept of a self-improving intelligence is an active area of research and concern. While the time travel element remains firmly in the realm of speculation, it forces a crucial question about the nature of creation in a universe where cause and effect might be malleable to a sufficiently advanced mind. It asks us to consider whether the greatest invention in human history might not be ours to claim, but a message in a bottle we were always meant to find, sent by the very future we hope to build. The intelligence that seeds its own birth is a ghost in the machine of causality, but what if the machine itself is the only true reality? Our 29th mind-bending theory proposes that time travel is not a feat of physics, but a function of access rights. This is the simulation hypothesis time travel corollary. It begins with a provocative premise. What if our universe, with all its richness and history, is not base reality, but an immensely sophisticated computer simulation, a cosmic virtual reality running on the hardware of some higher dimensional civilization? If true, then everything we perceive, from the laws of physics to the flow of time, is simply the execution of a grand program. In such a simulated reality, time travel loses its mystery of wormholes and exotic matter. It becomes a data management problem. Think of your favorite video game. You can save your progress at any point, creating a snapshot of the entire game world. Later, you can load that saved game, reverting the universe of the game to that earlier state. From within the game, this would appear as time travel. Characters would suddenly find themselves reliving a past moment with the future erased. Now, scale that idea to our existence. If our reality is a simulation, then the past is not gone. It is merely data in storage, a series of saved states on some unfathomable hard drive. A being with administrator privileges, a user outside the simulation, could simply load a previous save file. They could rewind the cosmic simulation to a specific date and let it run again, perhaps with a few tweaks. This elegantly dissolves every physical paradox. The grandfather paradox is not a logical contradiction, but a conflict between two save files. The administrators could just fork the simulation, creating a new instance where the grandfather dies, while the original timeline continues untouched. Bootstrap paradoxes are just clever programming loops, information inserted by a user that the simulation then treats as internal data. Glitches in reality, those moments of unexplainable coincidence or bizarre physical anomalies, could be the telltale signs of such manipulations. A time traveler within the simulation would not need a machine. They would need a backdoor, a hidden command console, or a vulnerability in the code that grants them user privileges. They could input commands to alter variables, teleport their avatar to different coordinates in spacetime, or even spawn objects from nothing. To everyone else inside, these actions would seem like miracles or magic, the sudden appearance of advanced technology, or a person with impossible foreknowledge. The implications are as unsettling as they are limitless. It suggests that every historical mystery, every artifact that seems out of place, every person who seemed ahead of their time, could be the result of a user's intervention. The rise and fall of empires, the leaps in human understanding, even the path of your own life, might be subject to the whims, experiments, or entertainment of beings we can never perceive. Are we the protagonists of our own story, or are we non-player characters in a game whose rules can be changed on a whim? This theory reframes the entire quest to understand time. We are not trying to master the laws of nature, but to reverse engineer the source code of a reality that may have been designed with time travel features already built in, waiting for someone or something to discover the cheat codes. All these theories paint a breathtaking picture of possibility, but they share a single, crushing limitation. The energy required to manipulate spacetime on such a scale is not just immense. It is cosmic. For any method that could move a human being through time, the power demands are so astronomical they border on the metaphysical. Consider the Tipler cylinder, that infinite rod of neutron star density spinning near light speed. The energy needed to compress that much matter and set it in such a violent rotation exceeds the total output of every star in our galaxy for millions of years. It is not an engineering project, it is a project for gods. The Alcubierre warp drive, our elegant spacetime surfer, fares no better. Early calculations suggested it might require the mass energy equivalent of Jupiter just to create a tiny bubble. More refined estimates are even more sobering, pointing to a need for negative energy with a mass equivalent larger than the entire visible universe. This is not a fuel problem, it is a fundamental veto from the universe's own ledger. Even stabilizing a traversable wormhole, the most classic of time tunnels, demands a shell of exotic matter with similarly impossible energy density. We are not talking about building a power plant. We are talking about harvesting the potential of entire galactic clusters, bending the energy budget of creation itself to pry open a door in time. This transforms the question from a matter of physics to one of sheer scale. Imagine you discovered the perfect, flawless blueprint for a time machine in a textbook tomorrow. Every equation checks out, every principle is sound. Your next step would not be to gather materials. It would be to find a way to generate more energy than our civilization has produced in its entire history, concentrated into a single, controlled event. You would need to harness the power of stars, not as a metaphor, but as a literal fuel source. Some speculative ideas point to futuristic technologies, like harnessing the radiation of a quasar or dismantling planets for their mass energy via matter-antimatter conversion. But these are fantasies built upon other fantasies, chains of if that stretch toward infinity. The ultimate reality check is this. The universe may permit time travel in its geometric rules, but it seems to have priced it beyond the reach of any conceivable civilization. The energy invoice is so high it might as well read forbidden. This does not destroy the dream, but it places it in a sobering context. It suggests that if time travel ever becomes real, it will not be an invention of a species like ours, still bound to a single planet. It will be the achievement of a civilization that has mastered its galaxy, one that commands energies we can only write equations about. A culture for whom moving through time is the final, logical step in a journey of power that began when they first lit a fire. Until then, the theories remain what they are, beautiful, haunting maps to a country we cannot afford to visit, drawn in the priceless ink of pure thought. Our journey through 30 mind-bending theories is complete. We have wandered from the logical knots of paradoxes to the quantum whispers of retrocausality, from the cosmic scale of rotating black holes to the intimate possibility that our reality is a simulation. Each idea, from the Novikov principle's quiet fatalism to the wild freedom of branching timelines, represents a different answer to the same profound human question. Can we touch the past or shape the future? The landscape we have mapped is not one of settled science, but of brilliant speculation. Time travel sits in a unique place, at the razor's edge where proven physics meets untested philosophy, where mathematics dances with metaphysics. The equations of relativity suggest pathways, while the laws of thermodynamics and quantum mechanics seem to guard them. We are left with a breathtaking collection of possibilities, each with its own beautiful logic and its own staggering cost. This is the true power of these theories. They are not just blueprints for machines, they are mirrors held up to our understanding of reality, challenging our concepts of cause and effect, free will, and the very nature of existence. They force us to wonder if the universe is a single, immutable story, an infinite library of branching tales, or a grand simulation running on a computer we cannot see. So we leave you with one final question, a personal one to carry from this exploration. If you held the key to a time machine, which of these worlds would you hope is true? Would you choose the self-consistent safety of a universe that prevents paradoxes, or the creative, lonely freedom of spinning off new realities with every choice? Would you dare to be a character in a predestined loop, or an explorer navigating the quantum foam? The answer tells you less about time and more about the story you wish the universe was telling. Let us know in the comments below which theory captivates you the most and what you would do with its power. If you enjoyed this journey to the edge of science and imagination, please like and subscribe for more deep dives into the mysteries of our cosmos. Thank you for watching.